the space where the measurement takes place. Such that the sum of all the outcomes is equal to the identity. The Born rule is what relates these two elements, these two theoretical elements, with the things that you see in the lab, which are probabilities. And finally, you have the axiom of system composition that tells you that, well, it's a bit involved, so I'm going to expand it. This axiom tells you not only that the Hilbert space of a composite system of A and B is not just the tensor product of the Hilbert spaces, but also it gives you some prescription for what it means to have a local measurement in this joint space. So in particular, it tells you that a local measurement in system A will be some operator that acts only non-trivially on this A part, and a local measurement conducted in B system, when viewed as a part of a joint system, will be something that acts only non-trivially on system B, on this Hilbert space here. And also gives you a prescription for local state preparations. If I prepare state psi in A and state phi in B, then the joint state is going to be a tensor product of the two states. Okay, the reason why I am going through this level of detail that normally when considering quantum information is because a couple of months after we put the paper, we got a comment by Finkelstein, who claimed that our result is not fully general. It doesn't apply to quantum theory in its full generality because we're making an extra assumption. And by this, he meant the tensor axiom. Now, so he says some other things that I will address at the end of the talk, but I want to focus on this one. Well, the first thing is that we didn't invent the tensor axiom. We learned it. We learned it in usual books, standard textbooks on quantum mechanics, and you can come up with. Okay. Of course, this is not well. Let's say to make a man of steel out of the argument of Finkelstein, right? I mean, the fact that we learn it doesn't mean that it's really fundamental for quantum mechanics, and perhaps it's just to paraphrase this book, a modern development, right? That is some sort of theoretical fashion that we use nowadays, this crazy thing of using tensor products to model different Hilbert space composition. So what my co-authors and I did was to go to the root of all evil, which are the first two books ever published in quantum mechanics, which are the Principles of Quantum Mechanics by Dirac and the Mathematical Foundations of Quantum Mechanics by John von Neumann. And we found in both books, these authors postulate that system composition is defined through tensor products. So this thing is not, this axiom is not an extra assumption. It is part of the definition of quantum mechanics. Quantum mechanics from its early beginnings was a theory that was devised to deal with many systems at the time, and system composition was defined through tensor products. Now what happens is that in some areas of physics, it doesn't make sense to regard the system you're dealing with as composed of many subsystems, perhaps because in some situations you cannot access them individually. So you don't have to invoke this principle, then you can simply ignore it. And this is probably the reason why some textbooks actually on quantum information, some of them modern, you didn't mention this principle, the tensor product principle. The fact that they don't mention it doesn't mean, of course, that it doesn't exist. Now, I keep trying to make a man of steel of Finkelstein's argument. He didn't say this, okay, but suppose that he had heard this counter argument of ours, and they said, well, that may be the case. It may be that tensor products are part of the defining actions of quantum mechanics, but so what? We know that quantum mechanics is not a fundamental theory, and most likely it comes from a more fundamental theory, which is quantum field theory. And in quantum field theory, you don't model space-like separation through tensor products. You model it through commutation relations. Okay, there are no tensor products in quantum field theory. So if you're going to prove a theorem and claim that it has some sort of universal validity, well, it doesn't make sense that it's just proven through in a class of theories that we already know that do not hold in general. And that would be a good counter argument. The thing is, he will be wrong, okay? But I have to say that I've heard this opinion very often. The idea that there are no tensor products in quantum field theory. It's a very common view, even in experts in quantum field theory. But if you start investigating the matter, you find that there are tensor products in quantum field theory. They just appear in a kind of subtle way. Now, when I prepare this talk, I prepare some slides explaining where these tensor products appear, but I think it will be deviating us too much from the topic of the discussion. If any of you is interested about that, at the end of the talk, I can stay some more minutes, right? I mean, and explain you, but for the moment, I would like to continue. I just want to say that in experiments in which you're dealing with different agents that are conducting measurements in some bounded space-time regions, and assuming that those regions are space-like separated, if you model this experiment with quantum field theory, you can assume that there's a tensor product structure between these systems. which is the only thing that I need for the things that I'm going to talk about. Good. So these are the axioms of quantum mechanics, and one of them is an axiom that that made some of the founders of the theory very suspicious, and it was not the tensor axiom. It was the first one, actually. So at the beginning, in the 1930s, Erwin Schrödinger was not satisfied with the appearance of complex numbers in the formulation of quantum theory. And in order to understand why, you have to think in which kind of situations you have complex numbers in classical physics. So complex numbers appear, for example, in electronics. They appear because describing currents in a circuit with a complex phase, and this simplifies the resolution of the dynamical equations of the circuit. They also appear in electromagnetism because describing electromagnetic waves with imaginary exponentials simplifies the computations. They appear in general relativity because describing metric perturbation with complex numbers, etc., etc., etc. And more generally, whenever we're confronted with a weird goo described by a linear differential equation, then the usual reaction by a theoretical physicist to try these ansatz. And that's placed essentially, to my knowledge, the appearance of any complex number in classical physics. But of course, all this is a mathematical trick. It's a trick that simplifies the calculations, but at the end of the calculation, the last step is always to take the real part of whatever it is that you calculated. Because at the end of the day, the electric field, the magnetic field, the intensities and the metric, they're all real quantities. So that's what probably what puzzled Erwin Schrödinger, the fact that the word complex, the presence of complex numbers already appeared in the definition of quantum mechanics. It was not just some trick in order to calculate things, but it seemed to be have some sort of fundamental character. And he wondered if he could make this theory somehow real. I'm going to say something that is pretty obvious, but if you take any mathematical model that uses complex numbers, then you can turn it into a real model. And I know that only uses real numbers just by replacing any occurrence of a complex number by two pairs of real numbers, which is the real and the imaginary part. Okay, this is completely trivial, right? You get a mathematical model that has the same predictive power and also the same complexity, but by doing this, you may lose the structure of the original model. And in our case, when I think, or when my co-authors and I think about the realification of quantum mechanics, the structure we want to preserve is the bracket structure of quantum theory. So we want to have still the same structure that we have here, but we want to have real numbers. Now, if you do these two things, you end up with some theory that also we didn't invent. It's been around in quantum foundations for a long time. It's called real quantum mechanics, which is a family of quantum theories. They're quantum because they satisfy the 5 axioms. But they have the extra restriction that the elements of the theory, the brass and the kets, are all real entries, have all real entries. Now, what is this theory? How does theory look like? Well, a priori, you wouldn't know what to expect, because if you take the quantum formalism, and then you impose that all the elements have to have non-negative entries, then what you find is classical physics. And of course, you allow them to take any quantum value, you get quantum physics. So a priori, you would expect that this theory should be somehow in the middle, so have some classical features and perhaps some other quantum features. But actually, this is not the case. This is not the case at all. Well, first of all, if we were living in a real quantum mechanical world, then we could hardly notice the difference, right? I mean, because we'll be able to do quantum key distribution, quantum teleportation, or quantum computing. In this sense, real quantum mechanics is much similar to standard quantum mechanics than to classical physics. But it has some really weird feature, and we try to convey it. So consider a bipartite experiment. You have a bipartite system, and then you separate it, and you give one part to some observer, Ali, and some other observer called Bob. And now suppose that it happens to be a quantum system, right? I mean, in this case, a real quantum system. It's a real quantum 2-qubit system. So if Ali and Bob are living in a standard quantum mechanical world, that should be able to conduct these measurements here, the Pauli measurements. And these measurements will allow to estimate, if they compare the results, these coefficients here. They will be able to reconstruct the state if you have enough copies by comparing the measurement results. But if Alice and Bob live in a real world, in a real quantum world, they won't be able to do this, because they won't be able to measure this Y matrix, because at least in the standard basis, right? I mean, the second Pauli matrix is a purely imaginary operator, so they cannot measure it. And with measurements on X and Z, they won't be able to estimate this parameter here. Now you could think, well, maybe that this parameter doesn't play any role in real quantum mechanics. But no, it does, because while Y is not a real operator, Y tensor Y is a real operator. So in principle, you can measure it. And the difference is that in order to measure this operator in real quantum mechanics, you have to put the two particles together. And this is a really weird thing. It's a really weird feature that is not present neither in classical physics nor in quantum physics, in standard quantum physics. This is called non-local tomography, and it's something really, really strange, really, really remarkable. Now, is it possible to disprove real quantum mechanics? Well, I think it's better in order to illustrate why it's so difficult to do this, I'm going to introduce two characters. One of them is going to be called Conan, the complex quantum physicist, and the other one is going to call Regina, who is a real quantum physicist. And of course, the story starts when Regina makes this astounding statement. The world is not quantum, it is real quantum. Well, so Conan cannot stop thinking about Regina's words, and he starts coming up with ways to convince her, otherwise to convince her that she's not living in a real quantum world. Then he comes up with this argument. The simplest quantum model in quantum physics, in standard quantum physics, is a two-level system, is the qubit. And the state of a qubit is defined by three parameters. We would define the position of the qubit in the Bloch sphere. But in real quantum mechanics, because you can measure the second Pauli matrix, then actually the space state is not a sphere, but a circle. So any quantum state, any real quantum state of two levels can only contain two parameters. So if Conan were somehow able to conduct an experiment involving two-level systems in which he were able to encode three parameters, perhaps he could convince Regina that she does not live in a real quantum world. So he does exactly this. He goes to his lab and he conducts some experiment with photon polarization, and he convinces himself that he can indeed store three real parameters in the state of photon polarization. So he concludes that real quantum physics is wrong. But that doesn't convince Regina. Because she says, and this is her argument, it is true that two-level systems, real systems, can only store two real parameters. But it could be that simply that photon polarization does not have only two levels. It could be that it has four-level systems. Yeah, so it has four levels. If it has four levels, then it's not difficult for Regina to find some state, some preparation state here, or some number of states, and also some measurements that would reproduce all of Conan's statistics. Okay, so in this case, Regina is able to come up with a real quantum model that also explains Bob's experiment. So Conan's experiment. So Conan hasn't convinced her. But there's a hole in this argument, and Conan is able to expose it, because Conan is very quickly with numbers. Okay, and he really realizes that if photon polarization were actually a real quantum system of dimension 4, then he should be able to store more than three parameters, actually 9 parameters. So he wonders, he poses this question to Regina, how come that I can only store 3 when according to your theory, I should be able to store 9? But Regina has an answer. That's easy, because you're a bad experimentalist. So I guess there are many ways to explain how come that Conan is not able to encode so many parameters into a 4-level real quantum system, but one of them is simply that he doesn't know how to. Maybe the experimental setup that he has does not really allow him to do that, but doesn't mean that it's physically impossible. So again, Regina is not convinced. Now, during the following days, Conan comes with different prepare measure experiments in different dimensions and with really eccentric states and measurements. But in all these situations, Regina is able to come up with some real quantum model that explains exactly the same observations that Conan is making in his lab. Okay, now Conan is going to try something different. He says, well, perhaps a Bell experiment could help. Now, just in case we're not familiar with Bell experiments, I will very quickly introduce them. So in a Bell experiment, you have 2 or more parties, in this case 2, Alice and Bob, who are conducting experiments in separate locations. And by separate, I mean really separate, like perhaps several kilometers separate. The idea is that in this experiment, they're called Bell scenarios, or the idea of a Bell scenario is that we don't want to make any assumption about what process happens in each lab. So from the point of view of Alice, she's going to introduce some symbol, X, that you would call it the type of experiment she wants to conduct. And she will obtain some outcome, some output, A, that will be the outcome of the measurement, right? But we're not going to make any assumption of what this measurement is or what it is that Alice is measuring, okay? There's just one symbol that goes in and another symbol that goes out. And the same for Bob. Bob will conduct some measurement Y, and obtain some result B, but he doesn't know what kind of measurement he's conducting or which kind of system. Okay, so we know that they have the idea that behind this experiment there's a sort of bipartite state that they're measuring, but they don't know what this state is. They don't know what kind of system is, or they don't know anything. The only thing they know is the statistics that they can get, because if they repeat the experiment many times, they can do frequency analysis and then obtain each of these probabilities. The probability that they obtain the results A and B when they input X and Y. Now, perhaps this is not abstract enough, so I'm going to actually get concrete in order to get more abstract. Okay, let's go to the 2-2-2 Bell scenario, which is the simplest Bell scenario that there is. It's a scenario in which Alice has two possible inputs, and Bob has two possible inputs, and they have both two possible outputs. Now here I call the inputs of Alice 1 and 2, but it is a convention, it's a label, right? I mean, I could have called them green and blue or Monty and Python. It doesn't really matter, because they're just labels, okay? And this is the important thing. What I shouldn't do is call them perhaps a measurement of polarization in this direction, because I don't want to make any assumption really about what it is that Alice is doing, okay? So just the important thing here is that there are two different measurements. You can implement one of two, and she obtains one of two different results. So together, in this case, in this scenario, these people can estimate 16 probabilities if they do conducting of experiments. Now, once they collect these 16 probabilities, they can estimate what people in my field call the closer Horn-Simony Hall parameter, which is simply some linear combination of the statistics that they measure. And it turns out that if Alice and Bob's experiment is modeled using local classical physics, you can prove that this parameter, the value of this parameter, cannot exceed 2. But if you can model it with standard quantum mechanics, then it can reach up to 2 square root of 2. So there's a gap. And geometrically, what this means is that if you consider the set of all correlations that you can generate in a classical system, and you represent each correlation as a point in a probability space, and you do the same with quantum correlations, what you'll find is that the set of quantum correlations contains strictly the set of classical correlations, and the CHH inequality is a sort of witness that separates these two sets. Okay, so in 2015, there were 3 experiments conducted in different parts of the world, more or less at the same time. They were quantum optics experiments, and this experiment generated correlations that you cannot reproduce with any classical system. So these experiments do not, of course, they do not prove that quantum theory holds, but for sure, what they do is to refute classical physics. Okay, so let's come back to Conan. Conan is thinking about this, and then he starts dreaming that perhaps he could do the same with the real quantum mechanics. Perhaps he could come up with some experiment, some complex quantum experiment that would produce some correlation that is unachievable with real quantum systems. That for surely would convince Regina. Okay, the CHSH would not do, because actually you can maximally violate it with real quantum systems. So he considers this other Bell inequality. This is an inequality defined in a Bell scenario in which Alice has 3 measurement settings, Bo has 6 measurement settings, and they have, again, dichotomic outcomes. And this is simply the combination of 3 CHH parameters, one between measurements 1 and 2 of Alice and measurements 1 and 2 of Bob. Oh, sorry, yeah, Bob, yeah. Another CHH parameter between measurements 1 and 3 of Alice and 3 or 4 of Bob. And another CHH parameter between measurements 2 and 3 of Alice and 5 and 6 of Bob. The maximum value allowed by quantum mechanics of this functional is 6 times the square root of 2. And you can achieve it with qubits, with a 2-level system. But to achieve it with qubits, it's impossible unless Alice uses what's the word? Complex measurements. Okay, it's impossible that Alice achieve this value using only real measurements. Good. So Conan goes to his lab, conducts the experiment, and this time instead of describing the experiment to Regina, he just presents her the statistics, and he concludes that real quantum mechanics has been refuted. But this doesn't convince Regina either. Because again, what she acknowledges that if in order to maximally violate this system, this inequality with qubits, you need to use complex operators. There's also other ways to maximize the inequality, like for example, with 4-level real systems. And she finds actually some quantum state, some real quantum state, and some real quantum operators that again reproduce the same statistics as Conan's. And as before, for the following days, Conan comes with new Bell experiments, and in each case, they could conduct with standard quantum mechanics. And in each case, Regina can always come up with some theoretical real quantum model that reproduces exactly the same statistics. And actually, she can do this because of this paper here. Okay, this paper shows that the correlations that you can generate in a bipartite Bell experiment with quantum mechanics, you can always reproduce them with real quantum mechanics. Now, you may think that if you go to more parties, Bell experiments involving more than at least the two parties, like Alice, Bob, Charlie, etc., then you will be able perhaps to find a separation, a gap between these two theories. But this is not the case actually because of this other paper. And this paper made everybody depressed, at least in my environment, because of this paper, we thought that there was really no way to distinguish between these two theories. It could be that actually the world is real quantum, but we just didn't notice. Okay, so Conan desists from using Bell experiments, and they start considering something a bit more general than a Bell experiment. So one thing that Bell experiments have in common is that you always assume that there's some state that is distributed to all the parties involved, but you don't make any assumption on this state, okay? Then we're going to make an assumption. We're going to assume that it is actually the result of composing two different states. So I'm going to think of an experiment in which some bipartite state is distributed to Alice and to Bob, and some other bipartite state is distributed to Bob and to Charlie, okay? Now, Alice will be able to measure her part of this bipartite system in some way. Bob will be able to measure his two parts of these two systems, and Charlie will be able to measure this other part. Okay, but the important thing is that the machine, or this thing was, well, these two states were produced by independent machines, right? I mean, so they're independent states. Okay, this is the only assumption we make. Of course, we do not assume what these states are, what kind of system is, or anything like that, right? I mean, or we don't make any assumptions about what kind of measurements go on here, because if we make any dimensional assumption, we put like some cap of the dimension, then we won't be able to justify it in front of Regina. We have to come up with something better. So the only data that we can handle Regina are the observed data, right? I mean, the probability of obtaining the results A, B, and C, condition on X and Z. This is the thing that we can observe in an experiment. Well, in this case, Coran is successful because he can come up with some experiment that generates some correlations that Regina cannot replicate. So she graciously accepts her defeat. Good. Of course, the experiment that Conan comes up with is the subject of the paper that you found in archive at the beginning of the year. The scenario I described before is, we call it entanglement swapping scenario. It's not very original, and you will soon see why we call it like that. And let's try to get this scenario and try to model what kind of correlations you would expect to get if quantum mechanics was a good description of this experiment. Okay. Okay, so let's apply all the axioms of quantum theory that we have listed so far. So to begin with, to any physical system that corresponds to some complex Hilbert space. This means that there should be some Hilbert space for these particles, another one for this other particle, another one for or system. It doesn't have to be a particle. Another one for this system, another one for this other system. Now there should be a state. The state should be some ray in the Hilbert space that describes the whole bipartite, well, in this case, four-partite system. And according to the tensor axiom, this four-partite system is represented by the tensor product of the Hilbert spaces. And because of the assumption of source independence, because the states were prepared independently, right? I mean, we know that there is some state here, some other preparation here, then the joint state should be the tensor product of these two states. Okay, so note that for the moment, I'm not making any assumption about what these Hilbert spaces are. They could be infinite dimensional, or they could be two-level systems, or even one-level systems, okay? I'm not making any assumption, I just assume that they must exist because the laws of quantum mechanics say so. Good. Now, Alice is obtaining some result, and the only way to obtain a result is to conduct a measurement. So this means that in this Hilbert space here, there's some measurements, some projectors, a set of projectors for each possible value of X, such that if you sum over the outcome, the A's, then you get the identity. Okay, and the same happens here for Bob, and the same for Charlie. Okay, there's some projector operators acting on this Hilbert space for its value of Z, and when you sum over the C's, you get the identity. And finally, we apply the Born rule. Okay, we have that the statistics that these people are observing is the result of calculating the average value of these operators, the measurement operators, but over these particular states, this tensor product of states. And notice the tensor product structure is a bit weird because here the states are divided between the A, B, and BC, and B prime C. They're divided through here. But the measurement that Bob is implementing is actually acting over these two systems. Okay, so the measurements are not divided along the same tensor product structure. Now, these are the correlations that you would have gotten in standard quantum theory. In real quantum theory, you get exactly the same expression, but the only thing that changes is that you have to assume that these bras have to be real vectors, and that these operators here have to be real. But otherwise, it's exactly the same expression. Good. So now we have clarified what the scenario is, how you model it with real and complex quantum mechanics, and let's try to prove that there's a separation. To prove the separation in the entanglement swapping scenario, you have to consider a sort of bell-type scenario in which Alice has only 3 measurement settings and Charlie has 6 measurement settings. They both have dichotomic outcomes. And in this scenario, Bob has no measurement setting, sorry. His measurement has 4 outcomes, but I could label them with numbers from 1 to 4, but instead I'm going to label them with the labels that we use to denote the Bell states, the 2-qubit Bell states. Okay. Again, this doesn't mean that the output of this operation is a Bell state. It's just some classical outcome, but I'm just using Bell states, the labels of Bell states in order to label it. Again, it could be from numbers from 1 to 4. And again, the observed data is just simply this probability distribution. Good. So the experiment that we propose, that we're going to propose some complex quantum experiment, and this is going to generate some statistics that you can reproduce with real quantum systems. And the complex quantum experiment is this one. In this experiment, you distribute the maximally entangled 2-qubit state between Alice and Bob, and the maximally entangled 2-qubit state between Alice and Charlie. The measurement of Bob is going to be a Bell measurement, and the outcome is going to correspond to whatever projection he gets. That's why I decided to label the outcomes by the labels that we use for the Bell measurement, or the Bell state, sorry. Now, Alice needs to have 3 dichotomic measurements. They're going to be the 3 Pauli matrices. And Charlie's measurements, Charlie needs 6 dichotomic measurements, are going to be given by some linear combinations of these Pauli matrices. Okay. Now, we have all the information here about this system. You can use now the Bond's rule to calculate all the probabilities. I'm not going to do it because there are 288 probabilities. But the important thing is that it's a finite number of probabilities. This is a set of probabilities that you can estimate very well with a finite number of experiments. And the idea is to show that you can reproduce these 288 probabilities using a real quantum system. So the main result that we have in the paper, well, one of the main results is that if you consider any probability distribution they generated in this way, right? I mean, using real predictor operators and real states, then you can only approximate the distribution that we got from the two-level complex quantum system up to a point. Okay, there's a limit in how you can approximate this distribution, and this limit does not depend on the dimensionality of these Hilbert spaces. The Hilbert spaces that you need to invoke in order to produce this distribution. They could be infinite dimensional. Okay, if you go to infinite dimensional real Hilbert spaces, you won't be able to approximate this arbitrarily well. There's a limitation. Okay. The main result actually is a bit bigger because it shows you that not only you cannot approximate, you cannot approximate the complex distribution using real quantum systems, but you cannot do it if you allow classical randomness between the 2 state sources. Okay. Now you may wonder why we care about this. It's actually very important, a very important assumption. The first is related to the practical importance of this result. So first of all, if you want to conduct an experiment involving 3 experimentalists, Alice, Bob, and Charlie, you would imagine that at some point these 3 people will meet, perhaps not in person, perhaps in Zoom, but they will exchange information about how to conduct the experiment. This information, if it's, for example, through doves, for example, right? I mean, you would imagine that it should be classical and not quantum, right? I mean, but there should be information. So whatever inequality you come up with should be robust against these kind of things. A more technical reason would be, for example, that maybe they conduct the experiment in the same city and they're using the same power lines. And if there's some fluctuations in the electricity, maybe these fluctuations will affect both at the same time, but at the same time, you wouldn't expect the fluctuations in the power lines to distribute quantum correlations, which is classical correlations. Second reason is that if you want to conduct an experiment in which you need 2 independent sources to produce states, you would probably need some sort of clock that synchronizes the sources, that tells the sources, now you have to produce the states. And this clock, in principle, could introduce some classical correlations. So it's important that you're protected against this thing. And the third reason, in my opinion, is the most important one. It's also the most subtle one. Sorry, the subtlest one. Well, the thing is, if you introduce this model, you allow these two sources to be classically correlated, then you find that the correlations that you can generate in this scenario with real quantum systems are determined by an infinite number of linear inequalities on these probabilities, on the probabilities of the system. Okay, if you do not allow these classical correlations, then you find that the set that you get, the set of correlations that you get, is determined by polynomial inequalities on these probabilities. The thing is, using standard techniques from Bell inequalities, you can proving that well, it's very easy to see that proving that a system violates a linear inequality does not require you to invoke the IID assumption. It doesn't require you to assume that every time you repeat the experiment, you get the same probabilities. There is a cleverer way to check that the system violates a linear inequality in the probabilities that does not require this assumption, does not require actually calculating the probabilities. Okay, it's simply a simple protocol that you can do that involves different experimental rounds. Now, if we were speaking about polynomial inequalities, it doesn't work anymore. And in order to prove that a system violates a polynomial inequality, to my knowledge, requires you to make the IID assumption. Okay, requires you to assume that every time you repeat the experiment, you get the same result, and therefore you can estimate the probabilities, and then you can calculate whatever polynomial you wanted to calculate. Okay. Now, why is this a problem? Well, it's a problem that we require the IID assumption. The problem is that the IID assumption is not respected in reality. So in quantum optics experiments, if you detect a photon, then very often, well, for most detectors, there's a sort of window, small window, in which you cannot detect more photons. So actually, there are correlations between different experimental rounds. These are correlations that you can measure in the course of an experiment, so you cannot just postulate them away, right? I mean, you have to account for them. Good. So before I said that you cannot reproduce these statistics that of the system that I presented before with maximally entangled 2-qubit states using real quantum correlations. I'm going to sketch why this is the case. Well, the first reason, well, let's start with this is the experiment that I proposed before, and you may notice, well, you must know this, right? I mean, this is an entanglement swapping experiment essentially for the part of Bob, right? I mean, he's going to conduct some Bell measurement, and whatever the result is going to be one of these Bell states. The result will be that the state of Alice and Charlie will get post-selected to the corresponding Bell state. Now, it doesn't matter what Bell state these two people get. Alice and Charlie, with these measurements, will be able to violate the 3 CHH inequality maximally. Okay, maybe not the original one, but maybe some other variant in which you change the sign of one of these things, right? I mean, but they're able to violate it. Okay, just with this kind of observables. Now, in this paper, it is characterized with kind of complex quantum systems can maximally violate the 3 CHH inequality. Based on the ideas of this paper, we prove that if you were able to reproduce exactly the correlations of the complex quantum experiment using a real quantum system, then you can define two real CPTP maps, U and V, that acting on Alice's and Charlie's system will, post-selected state after Bob's measurement would turn the system into a 4-level system, a bipartite 4-level system. Okay, so this is important, and this is. I'm not assuming that whatever is inside the boxes is 4-dimensional, right? I mean, it could be infinite dimensional, but I can prove that there's a CPTP map that taking this infinite dimensional system as an input returns as an output a 4-dimensional system. Okay, so you can prove this because simply by virtue of the fact that the post-selected correlations maximally violate the 3 CHH inequality. Okay, so I can determine just by virtue of these correlations here. Good. And what are these states? What state do you get in the end? You get whatever the state Bob got in his post-selection tensor this other weird state. Okay, so the first 2 qubits, they have a 4-level system, each of Alice and Charlie. So you can read this as 2 qubits. In the first 2 qubits, they have a Bell state, and in the other 2 qubits, they have this weird state. It's a state that looks complex, but actually it's not complex. It's a real state, because this part here is the complex conjugate of this one. Okay, so everything seems consistent. You have a real quantum state. We apply some real map, and we get another real state. Good. Now, suppose that we had applied these UV operators, UV maps, before Bob conducted the measurement. Then, well, if you trace out these two systems, what you get is a separable state, right? I mean, it doesn't matter that it's correlated, it's a separable state. And if you apply some local real operators, what you get is a real separable quantum state. Okay. On the other hand, you have gotten the same state if you had allowed Bob to measure, and then you have traced him out, forgotten the outcome of the measurement. Okay. So from the point of view of Alice and Charlie, the state that they would have had, it would be the state that they had after Bob's post-selection, but weighted by the probability of the post-selection and sum over the possible outcomes of Bob. Now, because we have an expression for these states, and because we know what the value of this thing is actually 1/4, then we can calculate the sum, and the result is simply the maximally mixed state, on the first qubit of the output of this channel. And on the other side, you have this weird state that I discussed before. And here you get a contradiction. Now, it's difficult to see why, well, okay, it's not that difficult if you're used to this kind of things, right? I mean, but it's kind of subtle to see why there's a contradiction between these two things, because you demand that the final state should be real separable, and here we have a state that is real and separable, right? So why is there a contradiction? Well, there's a contradiction because although this state is separable and real, it is not real separable. You can express it as a convex combination of product of quantum states, of tensor products of quantum states, but you can express it as a convex combination of tensor product of real quantum states. It's really subtle, but it's the case. And the reason why we know that you cannot do it, you cannot express it like that, is because all real separable quantum states are self-PT. So you have a convex combination of real separable, products of real quantum states, and then you trace out one of the systems. Here you get the trace of a symmetric real matrix, so you get the same thing, because you get the same state. But if you apply a partial transposition on this state here, you don't get the same state, you get a different state. Okay, so you get a contradiction. So this implies that indeed, with real quantum systems, you cannot reproduce the correlations of the experiment that I described before. If you follow the proof, then you can derive a robustness result. It's really long, and I don't know, maybe it's not that interesting, right? I mean, it's a bit boring, the derivation. I'm not going to put it, of course. You get a robust result. But it's robust, but mathematically robust, but still it's not good enough for, it doesn't suffice to do an experiment. So in order to get a more robust result, we used some other techniques. So the thing is, it is undecidable. You cannot characterize fully the set of real quantum correlations. Actually, you cannot even characterize it approximately. Characterizing approximately the set of correlations is an undecidable problem. But what you can do is to define some relaxation of this set, some superset that you can describe actually efficiently using techniques from convex optimization theory. Okay, so using these techniques, we managed to find some linear Baire inequality for this kind of systems. That and we found some upper bound of the maximum value of this linear function of the probabilities. It is among all possible real quantum theories, and this value can be beaten by the system that I put you before. Okay, so you have actually in this case a big difference, or at least big enough for an experiment. Good. So there was an experiment. Shortly after the paper by Finkelstein, there was some paper that appeared in arXiv where some experimentalists from China, they claimed that, well, actually they did, they claimed to have violated the our linear inequality to issue superconducting qubits. Now, this experiment has advantages and disadvantages. The advantage is that it does not have a detection loophole, because the systems, there's no sort of there's not any type of post-selection here, right? I mean, you measure the system and there's no problem. It has a big disadvantage, because in this experiment, Alice, Bob, and Charlie, it's not that they're not space-like separated, but they're in the same chip. It's ridiculous, right? So actually, the authors had a really hard time to justify why the two sources of states that you need, that have to be independent, are actually independent. How do you prove this? But in the paper, the way they prove it is by doing local tomography. The tomography of the whole system. They estimate the density matrix, and then they show that it is very well approximated by a tensor product of density matrices. The problem is that that's cheating, because in order to accept the results of this tomography, you have to assume that complex quantum mechanics holds. But if you assume that complex quantum mechanics holds, then you don't need to conduct the experiment. To me, it doesn't make much sense, this experiment. Now, I'm going to speak really briefly about some experiment that hasn't appeared yet in arXiv. It's an experiment in which we also participated, but of course just with the theory. We found some other scenario with a similar linear inequality. It's a different scenario, right? It's a scenario in which Bob has a setting which has 4 possible outputs. so for possible values. And in this case, the output is not four-partite, or it's not four-valued. It can only take two possible values. Okay, in the thing is that in this system, we found some inequality that we thought it would be easier to violate with quantum optical systems. And this is what the people in Shenzhen did. And in this case, the cool thing about this experiment is that Alice, Bob, and Charlie are actually separated, physically separated by some, okay, they're not spatially separated, admittedly, but at least they're separated by a few centimeters, which is something. Notice that this is the preparation, by the way, of the two independent states. And notice that there's actually a line connecting the two states. This line corresponds to a classical clock signal to indicate the second source to also produce a state, okay? That's fine, because as I said before, our formalism also allows classical correlation between the two sources. Good. This experiment also has advantages and disadvantages. The advantages, of course, is that, well, there's still some locality loophole because in the choice of measurement settings, right? I mean, but at least the systems are separated and you can argue, or you cannot really prove it, right? I mean, but at least you can argue that the sources at least are independent. But the disadvantage is the detection loophole. For reasons that I don't understand, because they explain me, but I still do not understand. The setup that these people used doesn't register instances in which the outcome of Bob is equal to 1. In order to obtain the probabilities that we needed in order to apply our inequality, you have to obtain it using some indirect methods. Okay, so still they could prove the violation of the inequality, the other inequality that we had, but my opinion is cheating. Okay, you have to make a lot of assumptions about what kind of measurements you're implementing. Okay, the way I see these two experiments are just some stepping stones towards a fully convincing disproof of real quantum mechanics. So let's try to go back into the future. I don't have any doubt that this will come at some point, right? I mean, perhaps in the next few years. Suppose that it has already come, okay? Suppose that we conduct some convincing experiment that produce some correlations that you cannot reproduce or approximate with real quantum models. So what will this experiment mean? Well, for me, I believe that Kes and Brass are mathematical entities that we use to describe reality. They're not actually factual things. So for me, this experiment is just an experimental disproof of real quantum mechanics. That's for me is really good enough, because I've been following and I've contributed that much, right? I mean, to this formalism of generalized probabilistic theories. But the only three ones that I think that are kind of reasonable, that I could believe that a priori that I live in a universe described by them are actually the classical physics, quantum physics, and real quantum physics. Okay, and the others I think they're super artificial, and they look like toy models to me, right? I mean, but these three are fine. Classical physics I think is a really reasonable theory. It just simply happens not to be the case because of the Bell experiments conducted in 2015. Okay, and real quantum physics I also think that is a very reasonable theory. It says that in view of the experiments that have already been conducted, you tend to doubt that it actually holds. Okay. There's another interpretation. It could be that you're a bit of a fundamentalist, a quantum fundamentalist. You think that Kes and Brass are physical entities in the sense that there exists such a thing as the wave function of the world. In that case, you can interpret this result as a demonstration of the physical existence of complex numbers. It's completely, I think this interpretation is completely crazy, but it follows, right? I mean, you think that there exists such a thing as a vector describing the universe. The experiment proves that this vector has to have complex entries. I don't support this interpretation. I support the other one. It's not as funny, right? I mean, but I think it's more realistic. Well, Jesus, I hate this terminology. Okay, so finally, I would like to finish by going back to this comment by Finkelstein. Well, he makes two comments essentially on the paper. I find the paper a bit insidious, right? I mean, because at some point we don't really refer to this set of actions in the paper that you find in the archive. But we refer to it indirectly, we call it the standard quantum formalism. And Finkelstein doesn't call it the standard quantum formalism. He calls it the standard quantum formalism. Because apparently he doesn't think this is a standard, because he has concerns with this tensor product thing. Well, I already discussed this, okay? He's wrong. But he observes also another thing. He observes that if you actually drop this action that he doesn't like, then using the remaining actions, you can get a theory that actually reproduces quantum correlations. Using elements, states, and measurements with real entries. Now, what is the secret of this theory? And I'm going to finish very, very soon. It's very simple. You take the original theory, including the tensor action of the original complex quantum theory, and you want to eliminate all the complex numbers. So what is the simplest thing you can do? Well, whenever I see a complex operator, I'm going to replace it by a pair of operators. So one of them will be the real part of the operator, and the one, the imaginary part of the operator. And whenever I see a real cat, then I'm going to replace it by two cats, a pair of cats. One of them is a real part of the cat, and the other one, the imaginary part of the cat. And then you can notice something very funny, right? I mean, I think it's a funny property. If you suppose that you take the real part and the imaginary part of a cat and you put them one after the other in a column vector, then you find that the column vector corresponding to the real and imaginary parts of M acting on psi is the result of acting on this vector with this other matrix here. And it turns out that if the M is a projector operator, and the thing will be a projector operator too, if psi is a normalized state, this thing here will be, this real thing will be a normalized state as well. So you're able to reproduce everything, but now of course you have lost this thing, right? But still you preserve all this part thing, and everything's real. Everything is real, but of course you have to duplicate the dimension by 2. Well, if you think a bit about this, then you end up with what Wouters called the real vector space quantum theory with a universal quantum qubit. It's actually originally conceived by Stuckelberg in the 60s, in the early 60s. The idea is that you have some universal qubit that is correlated with any quantum system in the world. And when Alice conducts some operation or some measurement, then this operation or measurement is going to act on both her system and also this universal qubit. And the same with Bob and the same with Charlie. Now, of course, in order to prevent communication between the parties through this universal qubit, you have to restrict the measurements to have some very specific form that guarantees the commutativity, right? I mean, and the form that you get is exactly the one that you would get if you simply realize, make real, I mean, complex quantum mechanics. So, of course, by construction, this theory has the same predictions as complex quantum mechanics, and therefore you cannot falsify it within complex quantum mechanics. Now, from the point of view of complex quantum mechanics or standard quantum mechanics, you would call this a non-local real quantum theory. It's non-local because you don't have Hilbert spaces for Alice, for Bob, and Charlie, but there's one that is kind of shared by all of them. Okay, that's why I call it a non-local real quantum theory. To Stuckelberg's credit, I have to say that this is the simplest theory. That is the first 4 axioms that has real entries that you can find that in order to reproduce quantum physics. Okay, simplest in the sense of the one with the smallest dimension. Now, from a high level, is it strange? Is it unexpected that there exists a non-local real quantum theory that reproduces the predictions of quantum physics? I don't think so, because you can do the same with classical physics. And in this case, I present you my theory. I call it the classical computer with a universal pulley. This is a computer that whenever 3 experimentalists, Alice, Bob, and Charlie, want to conduct an experiment, it does some calculations and try to calculate what the probabilities of the different outcomes are according to the rules of quantum mechanics. He gets some conclusions. He uses a random number generator to generate some random outcomes. And then the computer uses the universal pulley to change the measurement outcomes on each of the systems. Now, it's a very stupid theory, but it reproduces the predictions of quantum physics, or standard quantum physics, using classical physics. And of course, it has to be a fine-tuned theory in order to prevent communication between Alice and Bob, but so was the other theory, okay? Do you think this theory is special? No, I think it's pretty boring and pretty trivial, right? I mean, I think the same about Stuckelberg's theory. Good, okay, so to conclude, what I've shown is that there exists a causal network that has a separation between real and complex quantum mechanics. This is very surprising because, as I said before, with Bell experiments, with the standard Bell experiments, you cannot distinguish the 2 theories. So it came as a surprise that you can actually use an experiment to refute it, to refute real quantum theory within complex quantum theory. And there have been 2 experimental violations of the real quantum inequalities that we came up with, but the conditions are not convincing for different reasons in both situations. And I'm going to stop here. Thank you very much.
Okay, comments, questions? Gleb.
Okay. I have 2 questions. First question is more technical. It seems when you have your systems with Alice, Bob, Charlie, then you have separability between A and B and C.
Yes.
And what about this Perez-Horodetsky separability criteria? Does it somehow applies to that situation, or are there some? So what one can say about this?
Let me share the screen again. Yes, actually, it's, the Perez-Horodetsky criterion is essential for the proof because the only thing we were using to model the fact that these things are separated. Sorry. Look for okay, no. Yeah, the only property that we're using to prove that this to prove the result, right? I mean, the property using our real quantum system is the fact that this state has to be self-PT, exactly. So the Perez-Horodetsky criterion normally tells you that applied to any matrix tells you that if you partially trace this part here, you should still get a quantum state, okay? But in principle, you could get a different state. But because in this case, we're dealing with real quantum states, real separability, right? I mean, then it's very curious, but actually the set of states that you can create, the set of separable states in real quantum mechanics has less dimensions than the set of all real quantum states. And in this case, the Perez-separability criterion gets stronger. It tells you that the state has to be self-PT.
Does it mean that this situation somehow refers to bound entanglement?
No, I don't think so.
Okay. And another question is more general. So here you, it seems you are talking about two copies of B.
Copies of B. No, they don't have to be copies. Yeah? These are two different Hilbert spaces. They can have different dimensions. This could have dimension 3 and this one infinite.
Okay.
Okay, I have a question. When you have these modified Bell inequalities, usually the usual Bell inequality is like between 2 and 2 root 2, whereas your inequality is like 10 to the minus 6 or something like that, if I understood correctly.
No, it's I'm going to show you now. Where do I have it? I have it. Yes, actually, damn it, I didn't put it. Well, okay. The inequality is enormous. It's a linear combination of
oh, I see.
3 CHZ inequalities, and yeah, the result is we obtain it numerically. Yeah, I don't know.
I see. Okay, so basically, it's the difference between 7. All right, so it's less than what? Oh, I see. So 7.6 to 8.4 is sort of your sweet spot.
Yeah, exactly. Yeah.
So what was the point of this epsilon? I didn't understand the epsilon stuff.
Yeah, so okay, so this proof, the proof that of this result is analytic. It just tells you that you cannot approximate it arbitrarily well. The proof is analytic, so in principle you can read it and understand it. It's very long and very boring actually. But you can read it in a finite time. You can read it in a reasonable time and understand it and get some intuition about why you get a difference, right? I mean, the proof here is based on the fact that our computer found some positive semi-definite matrix that has some linear constraints. Okay, so I could give you the matrix and you could verify that the matrix is positive semi-definite and has this linear constraints. The problem is that the matrix is like 600 times 600. Okay, so this is a proof that you couldn't fit in a paper, and of course a human cannot comprehend, right? So on one hand we have this result, right? I mean, that is something that a human can follow, right? I mean, on one hand, this other result that, well, maybe there's a way that human can derive this, but we didn't find it. Okay, we found a way to, the computer found a way to derive it.
Okay. All right. Questions from the Zoom participants. Oh yeah, it is found.
So what if we wanted to compare complex quantum mechanics with quaternionic quantum mechanics?
Well, there's a problem with quaternionic quantum mechanics, as far as I know. I'm not really an expert on this, right? I mean, but when you consider tensor products, you have signaling. So it's problematic with this. Now, there's this paper by Howard Barnum where he constructs some generalized probabilistic theory that has as local states quaternions, okay, the set of quaternionic matrices. And then he shows that under a lot of axioms, his theory is kind of unique, okay. Well, this is as a result, is not in archive yet, but my collaborators and I have realized that the correlation that you get in the theory of Howard-Barnum is actually those of real quantum mechanics. You cannot even reproduce complex quantum mechanical correlations. It's very weird. It's a really weird effect, but it's possibly, well, I don't really know. I don't really have an intuitive explanation. It's simply that the theory is the way it is, and then we could prove that it's restricted.
Thank you.
Okay, Matt, you have a question?
Yeah, I just wanted to ask, what's the status of trying to do a loophole-free test of this? Are you trying to do that, or is any experimental group trying to do that with a photonic system?
Yes, the people who contacted us to this experiment, we understood that they want to do a loophole-free Bell experiment. Loophole-free experiment to refute complex quantum theory, real quantum theory. It's complicated because Tony, I think, for example, doesn't think that is necessary. His argument is that because we are trying to compare complex and real quantum theory, so why should you imagine that Alice is going to communicate with Bob, space like separated? But I don't agree with him. I think that you have to, this is a possibility in real quantum theory, right? I mean, so we have to account for it, right? So I think it's important that Alice, Bob, and Charlie are separated. I understand that they can do it. I mean, these two here, they're very good research, very good experimentalists. They managed to the measure. Okay, for this experiment you have to conduct a Bell measurement. It's an incomplete Bell measurement, but the degree of fidelity that they got after doing entanglement swapping is unprecedented. This is really a world record, and they're convinced that they're confident that they can reproduce it if they separate the systems. So hopefully you will have something maybe in a couple of years.
So if I go back to your single qubit examples, so you can always represent the qubit. It's represented in a group theory language as a member of the SU2 group, and you know that that's the same thing as an SO3 group with a double cover. And so, have people thought about trying to, rather than just do, say, real valued alternatives of quantum mechanics, if you unpack the group into some higher dimensional groups that have simpler generators, is there work along these lines from sort of a group theoretic point of view?
No, it was kind of implicit, right? I mean, if you take the construction by Stuckelberg, the one that I showed before with the real and imaginary part, right? I mean, you get exactly that embedding, right? The standard embedding of complex matrices into real matrices. There's just one way to achieve the simulations of these kind of things. There's a simpler way, actually. Let me see. Let me go to that slide. The simplest way to reproduce whatever you like is simply to assume that the system is classical and it has a crazy dimension that actually is encoding everything. And of course, you can reproduce then any possible outcome. For this kind of experiments, they're not very complicated. Where you have to do this embedding of complex numbers complex matrices into real matrices is when you want to reproduce statistics of a Bell experiment. You have to do exactly this.
Yeah, so what I find interesting is it shows that some of the physics is different than just the mathematics, right? If you have mathematical construction, the way you realize physically seems quite important to this argument.
Well, the key is demanding that, demanding that the two sources are separate, okay? If you try to apply the standard construction and try to embed this the usual way, try to embed a complex system in the usual way with this structure, you lose the structure, you lose the tensor product structure. And that's what changes. You will get actually like some sort of a state that is correlating these two.
Okay, yes, Abhishek?
Yeah. So I want to ask if like the shared randomness that you have, like if you assume that like it is correlated with the measurement settings. So
it's the same, yeah. Okay, let me put it. Yeah, you have something like this, right? I mean, you can imagine that it's transmitted to the measurement setting, right? I mean, so yeah.
Does it would that modify any of your results, or is it robust?
No. Okay. So if you assume that this randomness also affects the measurement settings, you can always simulate it by simply affecting the states, right? I mean, you imagine that it goes to the state, then the state goes here, and then it affects the apparatus, the measurement apparatus, right? So this model already covers the fact that there's a randomness between the measurement apparatuses.
I think we had one more Zoom question. Go ahead.
Yeah, is it me? Yeah. So I was wondering, in terms of computing and complexity classes. So real quantum mechanics can achieve universal quantum computation, right? So yes. This result, but still according to this result, there is a scenario where the real quantum mechanics cannot achieve the certain correlations. So
yeah, because we're separating the things, right? The sources, right? I mean, but in a quantum computer, there's no reason to separate sources, right? So that's why it doesn't matter.
Okay. Yeah. Okay. Okay. Yeah. Sorry.
Okay. Any more one more last question?
Yeah, I have
my last one. Yeah.
maybe just a clarification. You were saying something about the difference between assuming IID and not assuming IID, and I wanted to understand what you said there a little bit more. Can you just revisit that point?
Yes. No, actually, it's a complicated thing, right? I mean, and it went very quickly. So because I don't have slides, but okay. Yes. So okay. So suppose that every time I conduct an experiment, one round. Okay. Before I conduct the experiment, there's some probability distribution of the possible results that I get, right? I mean, I assume that this probability distribution exists. Is that I don't know what it is. Okay. Now, what could happen is that in the second round, I get some other probability distribution simply because maybe the source prepared different states, right? I mean, still, I know there's a probability distribution. It doesn't have to be the same. Okay. But it can be worse. It can be discorrelated, right? I mean, with the previous one, right? I mean, because it could be that the measurement setting that Alice chose here is going to influence somehow the state that you had here when you go to the second round. Okay, you can have these kind of correlations, right? So you can really assume IID. Okay. Some people do not have any problem in assuming IID, and some people conduct experiments. They assume IID, they check the polynomial inequality, but in my opinion, they shouldn't, because you have this problem. I mean, this is technical problem in all the experiments that I've seen. These are not IID, and you can actually measure it. So you shouldn't assume something that you can actually disprove.
Okay, so the problem is really that these things are non-Markovian. If you dig into the details, that's what you're saying.
Yes.
Okay.
Yes. And it's not obvious, but if everything is a linear inequality, you can devise a game in which you simply well, it's very simple. You simply measure randomly and assign some sort of a score system. You go adding the scores, you divide, right, or you multiply the scores if it's a 0-1 thing, right? I mean, and at the end, it doesn't really matter that there's different realizations of these probabilities or that they're correlated. At the end, the statistics that you get are still limited by the inequality that you had initially, right? I mean, so this allows you to get well, actually, this allows you in the standard Bell experiments to prove to discard real quantum theory. So to discard classical physics, right? I mean, because in those experiments, it's important also not to assume IID, because why should the classical physics be IID? So all techniques, they're not trivial. So you really have to go to the papers and understand why this happens, right? I mean, why you have this line here.
Okay, why don't we thank Miguel again for this nice seminar. If you were here, we'd invite you to lunch, but considering you're not here, we'll have to have lunch without you, but we'll be thinking of you.
Yeah. Thanks anyway.
All right.
Anyway, it would be dinner for him. We owe him a lunch.
All right, very good.
Good night, guys.
Have a great.
Thanks.